Hello everyone, we will be covering bubble sort in this video. We will discuss the concept of bubble sort, its implementation, and also discuss the pros and cons of this sorting algorithm. So diving right in. So what we do in bubble sort is, we start picking each index one by one starting from 0. So pick index starting from 0. Now let's say that the index that we have picked is I. So we will compare the elements at I and I plus 1. Now based on their magnitude, we will sort these two elements and then we will move to the next index I plus 1. Then we will pick its adjacent element which is at index I plus 2 and compare these two. Then we'll move to the next index which is I plus 2, compare the adjacent indices and move on. We do this till we reach n minus 1. So we start from 0 and we pick each index one by one till we reach n minus 1. Now once we have done this, we say that we have completed one pass. And at the end of one pass, what we expect is our largest element should be in its correct position. And the correct position is obviously the last index. So if we are sorting the array in ascending order, the correct position for the largest element in the sorted array is going to be the last index. So now that we have completed first pass, we are going to perform this whole exercise once again. We are going to pick elements starting from index 0 to n minus 1 and compare the adjacent elements and sort them accordingly. So when we complete this whole exercise again, this time we would have completed second pass. And by the end of the second pass, we expect that the second largest element would have reached its correct position in the sorted array. So the correct position for the second largest element is going to be the second last index. So the second largest element by the end of second pass would have reached its correct position. Similarly, we are going to perform this whole exercise again. And once we do it, we'll complete third pass, third largest element reaching its correct position. So by the end of n minus 1 passes, where n is the total number of elements in the array, after n minus 1 passes, all elements would have reached their correct position in the sorted array and the final output array would be sorted. So the algorithm right now might not be sounding very intuitive, or you might not be able to perceive that how this algorithm is able to sort the array. So what we are going to do is we are going to pick one example and use this algorithm on that particular example. And I'm pretty sure that after seeing that example, you'll be able to appreciate that how bubble sort is able to sort the array, and you'll find the sorting algorithm very intuitive after that. So let's pick an example: 70, 40, 60, 20, 10. Now let's start pass 1. So let's start picking indices from 0 and move till the last index, and let's start comparing the adjacent elements. So first we'll pick the 0th index and we are going to compare 70 and 40. Now 70 is larger than 40, so obviously these will be swapped. So our array would be 70, 60, 20, 10. Now in the second step, pick the next index which is 1. So we'll pick this index and we'll compare the two adjacent elements. So we'll compare 70 and 60. 70 is again greater than 60, so these will be swapped. So the array would look something like this. 70 will be swapped. So this is how the array is going to look like. Now we'll move on to the third step. In the third step, we will pick the next index, which is second. Now we'll compare index 2 with the element at index 3. So we are going to compare 70 against 20. 70 is again bigger, so you will swap. Last step. In the last step, you're going to pick the next index. Next index is going to be index 3, and you're going to compare the elements at index 3 and index 4. Again, 70 compared to 10. 70 is larger, so swap. 40, 60, 20, 10, 70. So with this, we have completed pass 1. And by the end of pass 1, you can easily see how the largest element, which was 70, has reached its correct position in the sorted array, which is the last index. Now let's begin pass 2. So pass 2, again we start picking index 1 by 1, starting from index 0. So we pick index 0, 40 compared against 60. So these are already in their correct order, so no action, these won't be swapped. So array would look something like this. Now step 2, pick the next index, which is index 1. So now we compare 60 against 20. 60 is greater than 20, so we'll swap these two elements. Step 3, pick the next index, which is index 2. Compare elements at index 2 and index 3, which is 60 and 10. 60 greater than 10, so 60 and 10 will be swapped. Now next step, pick this index and we will be comparing the adjacent element, so 60 against 70. These are in correct order, so these won't be swapped. So the array would look something like this. So this is the end of second pass, and you can easily see that by the end of second pass, the second largest element has also reached its correct position, which is the second last index. Now we'll similarly perform pass 3. So you can easily see how after pass 3, 40 will reach its correct position. Our array would look something like this. At the end of pass 4, 20 would have reached its correct position. And at the end of pass 5, we would have a sorted array. So actually we do not need to perform pass 5. So if there are n elements, we need to perform n minus 1 pass. Also, there's one more thing which you can notice is that we can reduce the number of comparisons in each pass. So here we had to perform 4 comparisons. But in the second pass, our last comparison was actually not adding any value, because we know that 70 is the greatest element and it is going to be at the last index. So whatever we have in second pass at the second last index does not make sense that we compare it with 70. 70 is already the largest. We know that. So we could have avoided this fourth step and perform only 3 steps. Now in the third pass, similarly, when you would have reached this index, it wouldn't have made sense to compare 40 and 60. We already know that 60 is the second largest element, and in the last step it reached its correct position. So comparing 40 with 60 wouldn't have added any value. So we would have avoided two comparisons. One is 40 with 60, another is 60 with 70. So for pass 3, instead of 3 comparisons, we would have only performed 2 comparisons. Similarly, for pass 4, we would have performed 1 comparison. So the total number of comparison that we perform in each pass can reduce by 1 as we keep on moving to the next pass. So what I'm trying to say is that pass 1, we perform 4 comparisons. Pass 2, we perform 3 comparisons. Pass 3, we perform 2 comparisons. And pass 4, we perform only 1 comparison. So now if we generalize this, let's say there are n elements. Pass 1, we will be performing n minus 1 comparisons. Pass 2, we will be performing n minus 2 comparisons. Pass 3, we will be performing n minus 3 comparisons. So on till pass n minus 1, where we will be performing only 1 comparison. So the total number of comparisons that we have performed are n minus 1 plus n minus 2 plus n minus 3 all the way till 1. And we know that sum of this arithmetic progression or sum of this series is n minus 1 into n minus 1 plus 1 by 2, which is n into n minus 1 by 2. So the total number of comparisons that we are going to perform in bubble sort are going to be of the order of n square, where n is the number of elements, which is essentially the time complexity of bubble sort, which is big O of n square. And as you can see that this is a in-place algorithm. That is, we have not used any additional helper space. We have just swapped the elements in the same given array. Since we are not using any additional helper space, the space complexity for bubble sort is big O of 1. So let's quickly write the code for bubble sort. Let's say that we are going to return a sorted vector and our method is called sort, and we receive a input vector, unsorted input vector. Let's call it array. Now we have to write this method which is going to return the sorted vector. Now we know that how many total passes we are going to perform. So if n is the number of elements, we need to perform n minus 1 pass. So int count is array dot size. So this is the size of the array. So the total number of pass that we need to perform is going to be count minus 1. So we'll do I less than count I plus plus. So this loop is basically going to control the number of passes that we are going to perform. Now in each pass, what we do is we pick indices starting from 0 all the way to n minus 2. So we do not pick the last index, because when we are going to compare the adjacent element, so there's no adjacent element, there's no element after the last index, so it does not make sense to pick the n minus 1 index. So we only pick till n minus 2. So we pick till n minus 2. But we also know that as we keep on moving further in passes, we can reduce the number of comparisons or the number of indices that we are picking. So we'll also reduce this by 1. We do j plus plus. So for pass 1, I is going to be 0. So we are going to go till n minus 2. For second pass, I is going to be 1. So we are going to go till n minus 3. So subtracting minus I has added the optimization that we discussed, that we can reduce the number of elements we are picking in each pass. So now in each step, what we do is we pick the element at the index and the adjacent index and we compare them. Now if the element at j is less than element at j plus 1, then we do nothing. But if the element at j is greater than the element at j plus 1, we swap. So we pass array j and j plus 1 to swap method, and it will swap the elements at index j and index j plus 1. That's all we need to do in our bubble sort. And once we've completed all this, at the end of all the passes, we'll have the sorted array and we can just return the array from here. Now one thing to notice here is that this bubble sort is a stable sorting algorithm. Now we are only swapping the elements if the element at j is greater than element at j plus 1. If element at j is equal to the element of j plus 1, we are not swapping. So we are not changing the relative position of the elements if they are equal. So in the sorted array, the equal elements are going to maintain their original relative ordering. Therefore, bubble sort is a stable sorting algorithm. Now there's another optimization. So let's quickly discuss that optimization as well. Let's take the array 1, 2, 3, 4. So how is the first pass for this particular array going to look like? We'll pick index 0, we'll compare 1 and 2, no action. Then we'll move to the next index, which is 1, compare 2 and 3, no action. Move to 3, compare 3 and 4, no action. So we see that in the entire pass, we have not made any action. And that is only possible if the entire array was already sorted. So what we can do here is that in each pass, we can keep a boolean which checks whether we have at least made one swap. If we haven't made a single swap in the entire pass, that implies that before the pass started, our array was already sorted. And if our array was already sorted, we do not need to perform any more passes. We can return from here itself because we already have a sorted array. So the optimization is simply keeping a boolean variable checking that if we have made any swapping operation in the entire pass, and if we haven't made a single operation, it implies array is sorted and we can return the that array itself without continuing to the next pass. We can just break from there. Implementing this optimization is very easy. So I would like you to take it as an exercise and try to perform this optimization. And I'll put the optimized code for reference in the description. If you feel stuck or if you're not able to write the code, you feel free to check the code in the description. But I would highly recommend that first try it on your own. Now, one more interesting thing. So this optimization will make the best case time complexity for bubble sort big O of n. And when is that going to happen? Let's say that the input array was already sorted. Now in the first pass, you're going to make n minus 1 comparisons, right? And after the first pass, you'll all realize that the array was already sorted. So you'll break from here and you'll return this array. So the total number of comparisons you performed were just n minus 1. So the time complexity is going to be of the order of big O of n. So this is just the best case time complexity after optimization. After optimization also, the worst case time complexity is going to stay big O of n square. Now what are the pros and cons of bubble sort? So it's a very simple algo. As you saw that it's very intuitive. When we tried it out on the example, we could see that it made a lot of sense. And also it is very simple to implement. You can see that the code for bubble sort is just a few lines, 5-6 lines. So it's very simple to implement, it's very simple to understand. It does not require any additional memory or helper space. And secondly, we also discussed that bubble sort is a stable sorting algorithm. Now, what are the cons of bubble sort? So it's not very efficient. The time complexity is big O of n square. So for very large data sets, this wouldn't fare well. So when you should use bubble sort? When your data set is not very large. In that particular case, the time complexity wouldn't matter much, but you'll be able to implement your sorting algorithm very quickly and you'll be saving on additional space usage also. So that's all about bubble sort. If you still have any doubts, do drop your doubts in the comment section below and I'll address it there. And I'll see you in the next video. Till then, take care and keep learning. Bye bye.